The second derivative of a function can tell you a lot about a function's graph's concavity, but can also tell us some information about the relative maximum and minimum values of the function. The second derivative test states that if f is a function and f prime of c equals 0, that means c is a critical number. C is an x value where possibly the graph has a relative max or minimum value. If you take that critical number, if you take that c and substitute it into the second derivative, and that second derivative is greater than 0, the value of the second derivative at that critical number is positive, then that critical number is a relative min. And you might say, well, if you substitute that and you get a positive number, why is it a relative min? Well, we're substituting that into the second derivative. And remember, in the second derivative, we're talking about concavity. This is saying that the second derivative is positive, so that means that the graph is concave up. And when a graph is concave up over an interval, if you have a critical number in that interval, that critical number would be a relative min value. So if you put a critical number into the second derivative and you get a positive number, that critical number is a relative min value. Likewise, if you put a critical number into the second derivative and you get a number that's negative, a number less than 0, it's a relative max. Because if it's less than 0 in that interval, it's concave down, and if there's a critical number in that interval, then that must mean that that critical number is a relative max. There will be times where you'll substitute a critical number into the second derivative and you'll get a 0, and that doesn't tell you anything. That in such cases, you'll have to use other methods to identify what's happening at that critical number. Let's do an example. Let's take a look at an example problem. Let's find relative max and mins using the second derivative test. We'll use the function f of x equals x to the third minus 3/2 x squared. To use the second derivative test, you first have to determine when the first derivative is equal to 0. The first derivative of this function is 3x squared minus 3x to the first power. And when you set that equal to 0 and factor a 3x out to the front, you find that values that make the first derivative equal to 0 are x equals 0 and x equals 1. Those are this function's two critical numbers. Let's test to see if those critical numbers are relative max or min values using the second derivative test. To use the second derivative test, well, you need the second derivative, so let's take our first derivative and differentiate again. The second derivative is 6x minus 3. Second derivative is 6x minus 3. So now I will evaluate both of the critical numbers in the second derivative. And realize if I get a value that's greater than 0, that means that it's a relative min. And if I get a value that's less than 0, that means it's a relative max. The first critical number I'll look at is x equals 0. When I evaluate 0 in the second derivative, I get a negative 3. Since it's negative, that tells me that x equals 0 is a relative max. X equals 0 is the x value of a point that is a relative max value in this function's graph. Let's take a look at our other critical number. Our other critical number was a 1. Let's substitute a 1 into the second derivative. That would be 6 times 1 minus 3. 6 times 1 minus 3 is positive 3. Since it's positive, it doesn't matter that it's a 3 necessarily. It matters that it is a positive. And since it's a positive, that means that x equals 1 is a relative min value. If the second derivative is greater than 0, that's a relative min. Let's take a look at the graph of f of x equals x to the third minus 3/2 x squared to verify our result. If you take a look at this graph, you can see that when x equals 0, that's actually the point 0, 0 on this function. We do have a relative max there. And when x equals 1, we're looking at a relative min.